Analytical Chemistry 1, Lesson 27. There will be many molecular systems you will use which have multiple reaction sites. The most obvious will be in acid-base systems. We looked earlier at malonic acid, which is diprotic. We solved the equations to find a quartic polynomial and found that one of its roots gave the right answer for the hydronium ion concentration. In the course of that, however, we observed that the hydronium ion concentration was very close to the same as the singly ionized form of the acid. So we made an approximation that the two are equal. What are the implications of that approximation? How will they change the equations we have to work with? Well, first of all, note what happens to the charge balance. We replace the HA minus with H plus. Look at our equation. H plus is on both sides. This can only be true if OH minus and A2 minus are zero. Now our chemical experience suggests that they should be very small. So within this approximation, if we are to declare that HA minus equals H plus, then they would be zero. Look at another equation, that for Ka1. We can replace HA minus with H plus and rearrange to get an expression for H2A. So take these two pieces of information, first that we set A2 minus equal to 0, and then that we make the above replacement for H2A, and insert them into the mass balance equation. This now produces a quadratic equation in just the H plus variable. When rewritten, it gives this equation that can be solved with the quadratic formula. We have reduced a quartic equation problem to a quadratic equation problem. So how does this approximation compare to the full quartic solution? Here is a table that compares these two expressions across a range of concentrations. You are perhaps not too surprised to find that again the quadratic is effective at high concentrations, but begins to fail as the concentration of the acid approaches the hydronium concentration in pure water. It is clear that the trend is similar, but the errors are greater, so that even at 10 micromolar the error is 13%. Very often we would speak of an error of about 5% being acceptable for the kinds of questions we would be asking, but there are still larger differences at higher concentrations. Now the feature we did not consider yet is how close are K1 and Ka2. Does this affect the accuracy of the approximation? Well, here's another table. We keep Ka1 fixed at 1 times 10 to the minus 3 and the acid formal concentration constant at 1 millimolar. We will vary Ka2 by starting at 1 times 10 to the minus 4 and decreasing it down to 1 times 10 to the minus 8. This time, the difference between the quartic and quadratic solutions is largest when the two Kas are close together. As they get further apart, the quadratic solution improves. The message here is that if the two Ka values are different by more than a factor of 100, then treating the acid as a monoprotic acid only introduces an error of less than 1%. When making approximations, here are some guidelines and suggestions. First, look at the charge and mass balance equations. Do you have any chemical reason to expect that any species mentioned there will have a negligible concentration? Or perhaps will one species be substantially larger than another? Make the approximation and modify the equations. Do they lead to a simpler result that allows you to calculate the concentrations? Once you've solved the problem, calculate the concentrations that are predicted from your approximate solution. Do they agree with your assumption? If so, you're good to proceed. And if not, you must go back, make a different assumption, and work through it again.